Alright, welcome to chapter 8, conservation of energy. You will find that in this topic, there are three main things. Tiga saja. Number one, we call it as non-isolated. Number two, we call it as isolated. And then, that will be the idea of power. Alright, how about 8.5? Changes in the mechanical energy, somehow they are correlated to the above, yeah? So let's now turn to the book. Now, chapter 8. The main concept of the term conservation here represent that the amount of the energy would be the same amount. Okay? Whereby the technique that we are going to see later is by using two techniques. Number one, if let's say non-isolated, there is a friction. Okay, 8.1 is actually referring to what if there is a friction. And 8.2 isolated system is considering there is no friction. That is the idea. Alright, now 8.1. Alright, the general idea first. Okay, so what we have seen earlier regarding work is actually a technique to transfer energy. Right, so we have seen earlier as well that when you apply force, there will be an effect and it will be a displacement. Okay. Now, how about other techniques? Okay. Another is what we call as mechanical wave. Right. So what is mechanical wave? For instance, sound. Now, another example. If you find that those who listen to very loud noise, in the long run might have trouble with their ears. Why? Because now energy has been used to drum on the tympanum, and over time, maknanya dekat drama telinga tu lama-lama jadi loose. Okay, so meaningful is done there. Another is, okay, mechanism of energy transfer is what we call as heat. This would be in physics too. Another matter transfer, electrical transmission. Okay, you have learned this in the idea of, for instance, power, electromagnetic radiation. Alright, now out of everything, you will find the general, there are three things that we are going, 3 to 4, okay, let me jot it down. Alright, we are going to study types of energy. Even though there are a lot of methods, work and such, you will find that when we modify or when we do calculation, we are going to look at number one, kinetic energy, types of energy. These are how the energy transferred. How. This is how the energy transferred. Okay. So aside of the work just earlier. Alright. And the effect is the energy possessed by the object would be in the form of kinetic energy, potential energy, where we can divide it into two. Number one, belonging to the spring. Number two, belonging to the gravity. Alright. Now, there was another actually a bit weird, okay, which would be energy loss. Okay, energy loss. Okay, so it's not in all of these three, but we're trying to say that you will see that probably aside of these three, there will be what we call as energy loss, where energy loss usually associated by the friction, coming from energy from the friction. Alright, in this book, you will find after this, the term used is a little bit different for energy loss. So this one, there will be a star. Now, overall, okay, the generic idea of this topic, therefore, get back to chapter 8, the title, energy is conserved. The amount is the same regardless what happens. It's just that it changes shape. How does it changes shape? By electrical transmission, by matter transfer, by work. Okay, and this topic will deal a lot regarding work. That's the idea. So keyword, if total amount of energy changes, then it's only because energy has crossed the boundary. Okay, energy has crossed the boundary. Now, in short, energy is supposed to be conserved. Patutnya sama. But you will find after this, somehow energy tu tak conserve because of this reason. It has crossed out. Dia keluar. Okay, so we are going to see that in the next version, whereby in what we call as non-isolated system. So the one which actually belongs to what we call energy loss is here, internal energy as described by the book. Okay. However, okay, you might as well use the other version coming from other textbook where we will consider this as what we call W and C, the term referred to non-conservative. Non-conservative. The rest are just conservative. Alright, coming back. Okay, hold on to this idea. We have this very large bloom of umbrella, the umbrella of the concept. Alright. Now, what you seen in this expression 8.2 is similar to what you learned earlier. For instance, the one that you have learned in the concept of work energy theorem, work is equivalent to the change of kinetic energy, is actually in the case whereby the rest are zero. Okay, there are no other types of energy involved, where you will find that, oh, the isolated system is reduced to only change of KE, change of kinetic energy equivalent to the work, right? Now, so since I did mention that this is a generic, so you might find that you are going to apply this and modify it throughout your calculation. Alright, before we did the modification, for your information, this is actually, again, I did mention earlier, this is actually work non-conservative, meaning that belonging to the energy loss by friction. Now, if you can still remember from previous topic, whenever we did calculate work by the friction, usually you will end with a negative product. Now, you will as well see that the work energy theorem, which actually come from this expression, meaning that the rest of the energy is now not there, okay, is because force, an external force, is added to the system, is applied to the system, making it becoming non-isolated. Maknanya ada additional force coming in, alright? And the fact is, dia punya kesan dia adalah object go through a displacement. And this work, okay, we find that there will be a change in the kinetic energy. Now, these expressions, when we simplify, by taking away the unnecessary energy, which is this unnecessary energy, we will find that our energy are composed of almost four types actually. Four types. 1, 2, 3. Okay, 1, 2, 3. And we can add one more, that potential energy has two types. Number 1, gravitational potential energy. Number 2, spring potential energy. Alright, now, interesting enough, the book here, okay, keep the internal energy as part of the system. Now, if you look at other books, they are doing it a little bit different. So, if let's say that you are referring as well to the other textbook, you will find that potential energy, kinetic energy is considered as within together as the system. However, the work non-conservative is outside. Jadi, effect dia adalah effect dia ya dari segi matematik. Work non-conservative ni akan ada negative value, while when it is here dia akan ada positive value. Cuma matematik kiri kanan lah maksudnya. Alright. So perhaps kita tak nampak lagi idea dia. Kita kena tengok calculation, then only we can see the effect of how the book dia do the calculation. Alright, let's look at 8.2 where it's now considering isolated system. But before we proceed, we are going to do a little bit of modification to the general expression earlier, so that at any time it can be isolated, it can be non-isolated as well. So, number one, before we proceed, what is isolated? Isolated in this case is referring that there is no friction involved. Okay, the expression that we're going to take into consideration is three things. Delta U, delta K, and also delta internal energy, whereby it's equivalent to work by non-conservative. I'm gonna write it in another version, whereby you will find that this version is available on the online as well, or other textbook. That delta kinetic energy, when you sum up, okay, adding with potential energy, perhaps we are talking about spring, perhaps we are talking about gravity. So there are two types as well, spring or potential by the gravity, will be equivalent to the work non-conservative. What I'm doing is I'm taking this to the other side, right? So when you are in this version, whenever there is no friction, just substitute non-conservative as 0, okay, or else calculate it, calculate the value. So in that sense, just now in the given example here, which is 8.4, you will find that there is no this consideration is whereby there is a book held at a certain elevation and then release. So in this case, you find that there is no spring, so 0. And there is no friction as well. So work non-conservative turns to be 0. So as you simplify, you arrive with this expression. Now, this expression is something that you have seen in high school. Okay, how does it looks like? Okay, the terms delta U just now, this is the delta U, sorry, the delta kinetic energy, this is the delta U. Right. When you rearrange, notice something. The final to be added up together and the initial to be added up together. Now, it's therefore this expression and this expression, it's also correct to say that energy final is equivalent to energy initial. So that is the idea or the main core that you have learned in high school when energy is conserved. It's just that for this particular book, it's writing it down in this different version where delta K plus delta U is now equivalent to 0 because the work non-conservative is 0. Understand? Alright, now, so which one would you use? You could either use the version that you have learned in high school, and for that, it's actually similar to what's given just now. That's one. If you are using this one, then you had to be extra alert on the type of energy involved. Type tu apa? Kinetic, potential, or perhaps involving potential from spring. Okay. Now let us look at example 8.2 where we have seen this scenario in the previous topic, which free fall. Now, besides solving using kinematic, we're going to see that we can use another 2 more methods. So this is the second method, satu lagi methods ya. Now, in the case of this topic, we are going to make use of what we call the expression earlier, change of kinetic plus change of potential equivalent to 0. However, you might note that expression that I have emphasized earlier is that I'm asking you to jot down in this version. Okay, in this version. And you will find in this scenario, the value of work non-conservative is equivalent to 0. Reason is there is no friction. So the question supposed to say is that ignore friction. Okay, or if air friction is not there, neglecting air friction. Now case is it's drop, so our initial velocity would be 0 from a certain height below. Neglecting air friction, determine the speed at a certain height below than the original release point. So in our case, it was from this H. Okay? If you are unhappy about the H, you can substitute your own number. For instance, mg times 50 meter. So this is 50 meter. Okay. And at a location below, you can again substitute any random number. Mungkin 25 meter. So you have 25 um, mg. So the same thing. Alright, so what you did after that, you will find that you jot down the energy here. So this is the energy belonging to potential. This is energy belonging to potential at this location. And what will be the kinetic energy? The kinetic energy would be 0 because this one is actually half mu squared. Now, in this case, dia kata tadi drop. So drop ni effect dia adalah U kosong. So this is 0 So if reflecting KE pun 0. Kinetic energy. Now at the location below than the release point ni, dia akan gain speed. Definitely dia akan gain speed, and because of the gaining in speed, you will find that it will have its own V. So that's the reason why kita akan put down the expression as half mv squared. Half mv squared. What about mgh? No problem. 25 mg. So in our case just now, by using this expression, feed in data ni. Feed in these two data. So you can see here, if I can label this as A, this is B. So this is B, this is A. Maknanya ini final, ini initial. So same as this one, B and then A. Alright. So this one belong to the potential energy, this one. So as you substitute the number, it will allow you to rearrange the expression in getting the value. And again, note that in our case here, the G is just a positive value of 9.8 because it's a scalar product. It's a scalar. Scalar, Take note on that. Alright, I like you to play around with this technique whereby you can choose two numbers as given, arrive with the V at this location B, and then repeat the question but using free fall technique, which means kinematic. You should arrive with the same answer. Now, this is the third method in calculating the same answer as A just now, speed. So we are going to use what we call as work energy theorem. Work energy theorem. Now, in using this, we need to identify what are forces that act on the ball. Accordingly, there is a single force alone. So what are the forces? The forces is gravitational force, which is mg. Okay, mg in the direction downward below. Now, another thing to note as well, that the delta R is also in the same direction. And therefore, we will find that when we substitute the force will be a product of mg, while the R would be delta R, okay, or perhaps we will be replacing it properly with the concept of delta y final minus y initial. Now, interesting to note that the angle between them is cos 0 because they are parallel in direction. However, considering the concept of delta y, which is equivalent to delta r, you will find that your answer will be a product of a negative product. Okay, now let's put in numbers here. Observe that just now, the final is 25 while the initial is 50. So indeed, you will arrive with a negative of 25. A negative of 25. But you might ignore this concept. Okay? What you can straight away do is consider the whole idea that it must be parallel or anti-parallel considering their angle. So in our case, the angle is 0. So go with this technique, you will find that you will arrive with the same answer as the above. Okay, so in conclusion, altogether, okay, calculating work version, we can use this technique or we can use the version of change of kinetic energy plus change of potential equivalent to work at non-conservative. But in this case, because there is no friction, yes, you can state it as 0. So any of these two methods work. Now, in example 8.3, you were given a situation where an actor attached to a string and supposed to swing. So, as he swing, something like this, okay, the curve motion, okay, so the back will remain, supposed to be remaining here, okay, remaining here. Now, the thing about the movement is that as overall, okay, there are a few datas here. So we are expecting him to swing, okay, swing, that's number one. Number two, when he swing, by the time he reaches here at the bottom of the curve, let's label that position. This is where he started and this is where he's supposed to pass through. You will find that at that position, we expect that the sandbag hardly lifted. So just about to lift, okay? That's the maximum weight we're supposed to put here. And that's the reason why they say here, it almost the normal force of the sandbag uh, almost goes to zero. So macam dia nak hampir terangkat lah. Kalau dia fully terangkat, then we will expect that this actor just drop to the floor. Jadi kita tak nak dia full terangkat. So that's the idea. Okay. So it's lifted but slightly. Slightly lifted. So that's the key word. Slightly lifted. Okay. And therefore the normal force approaching zero. Okay, approaching zero. Okay, before we go further, we need to look at the solution. We are going to consider there is no friction. So that's why both change in the energy, kinetic, plus change of potential equivalent to zero. There is no friction. Yeah? You are supposed to ignore friction. That's number one. Number two, the V final here is at the lowest position. And this is where he starts. Okay, he starts. So we are going to label the start and the lowest. Yeah. Now, accordingly, as we fit into our figure, we will find that our lowest is occurring at position B here, while the start occurring at A here. And as we fit in the Y, the height, the vertical height, it shows that the vertical height is V final at position B. Notice the B. And V final initial, sorry, Y initial at A. So this is at A. Alright. So we are trying to fit into what we call as the expression just now. And therefore our V final squared is now become 2G and then Y initial minus Y final. Alright, there's an issue here. Observe that V and R's a bit different, but you will find that this is the right version, yeah? This is the right version as you do your simplification. But nevertheless, let's look at how we are going to convert it into such. Another is, before we proceed, now from this expression, simplify it. So you'll find that you can cancel off the product of mass. And then you will arrive with this one. And later on when you rearrange the expression, you will find that V final squared is equivalent to S given. Quite different to this one. Quite different to this one. Now, I like you to cancel off this one. It's incorrect to have Y final minus Y initial. Okay, let's play around with partially substitute numbers. So let's say that he started here with at a distance of 5 meter. And by the time he reaches here, it will be 2 meter. Okay. So mathematically, we expect that Y final is 2 lower at the ground minus 5. Yeah. So just notice that this is an example. I'm going to rub it afterwards so that you can see the common sense. So 2G, the Y initial is 5 meter minus 2. So notice that on the right side is a positive product and therefore you can later on square root the number. But if let's say that it's Y final minus Y initial, then end up it's a wrong situation. So it's as if becoming 2 minus 5, which is way too wrong, right? So that's the reason why I did mention that this is wrong. So this is the right one. Alright, actually when you are here, is actually enough for generic question. Generic question sebenarnya cukup. Bahawa awak cuma akan lihat only the changes in the Y displacement enough. Okay, Y displacement sahaja, vertical Y sahaja, tak ada sengit-sengit. However, untuk fit into this question, dia nakkan you substitute together with the angle. So that's what we are going to do next. But again, bear in mind sebenarnya ini cukup. Ini sebenarnya cukup bahawa dalam general questions. However, kita nak buat masukkan angle. Alright, for that, kita tengok balik gambar asal. The original figure shows that dia membuat arc. Okay. So therefore, saya sketchkan this figure to indicate the condition, kedudukan dia masa dia mula-mula tadi berada di sini and then the final when it is here. Notice bahawa this is the string length. So R yang sama sebab tali itu digambarkan sebagai R. Jadi this is the vertical height just now and this is the vertical height. Jadi sekarang kita adjust sedikit ya. Now, it says that okay, ini kita labelkan A, ini kita labelkan B, ini kita labelkan C, and then the ground we label it as D. So, our previous expression, we are supposed to replace Y initial, Y final differences would be in a form of angle. So, accordingly, Y initial is here, which is equivalent to Y at B, okay, Y at B, and minus with Y at C. And we will find that this is actually equivalent to, so equivalent to the YBC itself. So notice that this, and then minus this, will be equivalent to this. Okay, equivalent to this. This thing. Therefore, to find this, okay, you will find that it's also correct if we can calculate the distance, jarak, from A right until C itself. Right until C. So from here until here. And then minus with A until B. YA until B. And doing that, okay, doing that means that we can get YAC here, A until C as R, minus until B as the product of, okay, if this is our angle, eh, if this is our angle, we will find that the length from here to here is equivalent to R cos theta. And that is the reason why we factorize. We have 1 R times 1 cos theta. Okay. So the difference, which is BC here, YBC here, is also equivalent to R times 1 cos theta. And this would be substituted into Y initial minus Y final. That's one. So you are going to end up with this expression. So this and this is equivalent to one another. Alright, so to conclude, okay, even though this expression look a little bit weird, okay, so don't worry much. What really important is you will find that changes initial minus final here is actually equivalent to just a vertical length between B and C. Okay, now let's have a look at example 8.4. Now in this example of 8.4, you will find there is an additional energy. What is it? Which is coming from the spring. Now, as given in the figure, okay, this is a mechanism where there is a spring here. So we call it as a trigger release spring. Now, spring is compressed to a position of YA. So this is YA just now being compressed. A projectile then, M, rises to a maximum position YC. Okay, this is what happened, okay. So when originally when it's at position B, mula-mula kita fill up the loaded gun lah, macam kita isikan dia, and then kita push the spring. Okay, so dalam cerita ni dia akan assume that when it's at equilibrium, spring tak compress, letak sahaja, this is how it looks like dekat B position dia. Yang ini kita akan assume as Y kosong. Dan kita compress, bila kita compress, you find that ada distance travel, macam you nampak bawah H now is negative, right? So itu yang berlaku lah. And then the moment you release the trigger, dia pun jump upwards. And then dia sebut sebagai maximum position. Maximum position ni is whereby masa dia sampai YC ni, V akan jadi kosong. Kenapa? Because similar to the concept of free fall. Dia akan pergi paling tinggi masa sampai ke kawasan tinggi sekali. Then kita akan kata dia akan buat turning point. Masa tu V akan instantaneous V at that position would turn out to be 0. Lepas tu dia pusinglah balik. Okay, downwards. Alright, so that is the situation. Jadi kita nampak ada satu lagi energy aside that what we have seen earlier. Kita kata kinetic nombor 1, potential nombor 2. Okay. And if you remember potential kita kira using mgh, mgy. So either way lah. And kinetic energy is based on the expression of half mv or mu squared, depend, right? And elastic potential energy is coming from the spring. So yang ini yang baru in this example, where we can calculate it based on the compression. Okay, the idea of the energy adalah originally ini adalah gambar ketika kedudukan dekat B. Okay, position. Y dekat B. So kita dapati bahawa there is no changes in dy and then there is no compression on the spring. And then dia static masa tu. Okay, tu je cerita dia. And then the moment kita compress dekat A, dia masih lagi static. So that's why kinetic energy is 0. Because dia static. Okay, this is static. Okay. And all the energy adalah dalam dua bentuk. Two shapes. Number one, elastic potential energy. Sebab dia compress the spring. Compress spring. So compress spring. Okay, so number one is static. Number two, it's compressing the spring. And number three, we find that there is a vertical distance travel here to downward. So that's why gravitational potential energy adalah dalam bentuk negatif. Jadi bila kita sum, kita tambahkan dua-dua ni, so we find that the total energy is this much, which is 100%. Okay. Now overall after this, kita akan nampak total energy ni remain the same. Same value dia 100, same value dia 100. It's just that types of energy bertukar. Masa dekat D, types of energy adalah purely dalam bentuk, what is it? Dalam ini adalah keadaan yang dia lalu balik. Bila dia compress, dia lalu balik dekat position B. Masa position B, what happen? Elastic potential energy and gravitational potential energy semua tukar bentuk. Okay? Okay, fahamkan bahawa situasi dia, masa originally kita load, kita letak dekat B. Okay, and then kita compress. Bila dia compress, it is at A. And then kita release the trigger. Bila dia release the trigger, dia akan lalu balik dekat point B. And masa dekat point B ni adalah, ini adalah YB again. Okay, where all the energy are fully converted into kinetic energy. Okay, fully kinetic. Jadi, kita akan nampak masa ni kita akan ada mass V kat sini adalah maximum speed sebenarnya at the location of B. Okay, and then by the time dia reach at C, YC, kita nampak remain the same in terms of the energy. However, semua dah fully converted pula. Dia semua tukar balik shape dia into MGH ataupun MGYC lah. YC. However, YC itu kita akan kira antara between B and C. Okay, between B and C. So that is the whole idea how energy is converted. Tapi baseline dia maknanya jumlah tenaga adalah sama ketika mana kita mula-mula membekalkan. How bekal? Kita dengan susah payahnya kita tolak, push the spring. Kita push the spring, compresskan dia. So tenaga kita now ditukarkan into the form of spring. So kita bentuk ni and also a little bit of potential energy tapi ada negative here. Alright, enough talking. Let's look at what does it want. Alright, ignoring all resistance. Determine the K value, spring constant. Okay. Now, spring constant, kita akan buat, what we are going to do is, we are going to consider two situations, A and C. Now, A and C, so this and the highest position. Okay. Now, in that sense, bila kita masukkan expression, since kita dah add on one types of energy, kalau originally, previously, kita cuma consider change of kinetic energy and then kita kata add dengan change of potential because of the gravity, maka kita dapat kosong kan, ataupun kita kata sama dengan word non-conservative. But because kita kata friction tak ada, there's no friction, maka straight away this one pun jadi kosong, zero as well. Tapi kita add on, so kita add on apa? Spring. Okay. Now, adding spring tak ada apa pun. So, you will find that between C, so C akan jadi final. C is now our final. And also A akan jadi our initial. Okay. Kinetic energy between C, maknanya kinetic energy C tolak dengan, C minus dengan A. Okay, kita tengok C dengan A. Now, at position C, the V akan jadi 0. Remember the idea of the turning back earlier when it reach maximum height? Okay. So here it's static kan, because dia tak bergerak. Kita push and then let it stay there. Then only kita pull the trigger. Jadi kat sini pun kosong juga dia punya U dia. So that's the reason why the energy change is 0. Okay, settle lah. Now, sekarang kita observe pula the positioning between C and A. So, C and A ni if, okay, kenalah tengok balik the value given in the question later lah. Okay, so just substitute V, Y, height dia dekat C dengan A. So, what we did earlier here adalah kita kena really very clear of this one. Between A and C. Maknanya B kita dah tak fokus pun, kita tak tengok pun. We just go straight away pada initial dan final yang kita dah decide. Okay. And then, how about the change in the potential energy belonging to the spring. Jadi kita tengok between juga positioning dia adalah C tadi and then the initial sebagai dekat A. Okay, sekarang tengok kenapa C ni kosong, 0? Because dekat C, there is no spring. Spring dah fully extended, maknanya at equilibrium. Compression dah no longer occurring. So that's the reason why it's 0. But how about at A? So kita notice bahawa at A, yes, kita telah pun compresskan dia. And then you might get confused. Should I include the negative or not? So kalau kita open up the whole idea of half K ni and then X macam ni, we will find that, oh, it's actually boleh terus X squared sahaja. So either it's compression or decompression, kita tarikkan dia ataupun kita compresskan dia, it will end up as a positive value of X squared. Yeah? And remember earlier, don't memorize, you just rearrange them, you will find that you will arrive with the answer lah. Substitute all accordingly. Okay, now to look at another, okay, saya nak tunjukkan satu lagi version whereby the whole idea when you arrange it as such sebenarnya very similar to this is K final minus K initial, okay, then plus potential, should I write as potential U lah so similar to your book. I might be writing as PE as such, okay. So final minus initial and then out of pen, so green, plus kinetic spring, initial final spring minus final initial spring, 0 Now, when I rearrange everything, you should notice that all the final are adding up together. Nampak tak? Plus, plus, plus. So, it's as if energy final, okay, tengok and then minus and also minus. Nampak tak? So, it's as if minus the whole total energy initial, which equivalent to 0. So what you are seeing, this expression of delta plus delta plus delta is really all about the total energy final minus total energy initial would be equivalent to 0. So meaning that energy final akan sama juga dengan energy initial. That is another way of looking of this topic. Jadi, kalau kata you rasa macam unhappy to use this expression, you can sebenarnya opt untuk guna the number 2 expression. Diorang ni sama saja. Okay? Alright, B, find the speed at B. At the equilibrium position. Okay, masa kat equilibrium position ada berapa types of energy. Equilibrium position at B here, kita nampak ada the energy of elastic potential energy. There is no elastic potential energy. The energy are purely dalam bentuk kinetic energy. So, since it's purely in the kinetic energy, we find that kita akan buat comparisons of energy. So here, the book choose between A and B. Now, for your information as well, kalau kata tadi previously, we can use the idea of energy final minus energy initial tadi. So, meaning that, okay, writing it as such equivalent to 0. Jadi kita akan pilih ini sebagai position B and then position A. Tetapi because energy are constant kan? Constant, and then kita nampak bahawa dia changes bentuk. Okay. Makanya it's also correct if you ambil at C. Anything, okay, as long as you nampak bahawa comparison. So for this case, because dia ambil A dengan B, jadi A ni akan jadi initial and then B akan jadi final. Okay, nampak ni final ya. Final ni dekat A, which is initial. Now going back to the initial A tadi, berapa kinetic energy dia? 0, tak bergerak. And then apa kata at the position of dia punya height pula potential energy. So potential energy dekat B, okay, kita tengok balik potential energy at B, dia Y is 0. Okay, Y is 0, that's why dia punya 0 lah height dia. And then MGH, MGY, okay, sama saja. Alright, so MGY dekat A from comparison kita dekat B final kita. So B adalah height dia adalah here. So from here until here. So minus mg YA. And then we find as well the final energy yang tambah tadi from the spring. Okay, so masa dekat B and also dekat A. Sorry, A. Alright, B. Okay, tengok B no compression. So half kx sebagai 0. And then at A, half kx squared So maknanya it's all about identifying dekat position tu macam mana. And then substitute accordingly. Masukkan ikut rumus sahaja. Masukkan ikut rumus. And then finally, just susun balik all the numbers that you have substitute into the expression. Getting the answer. And not forget the final units. Now, this is another example coming from another book, whereby we are going to see that we can solve by using the concept energy final minus energy initial equivalent to 0, provided there is no friction. So, it says here, use conservation of energy, where this conservation of energy is actually equivalent to the change of KE plus change of potential energy equivalent to 0. And we find that in the process of doing calculation, there is no, tak ada force yang lain lah. Tak ada external force. External force tak ada So masa external force tak ada, we can use this concept. Okay, kita boleh pakai rumus ni. Alright, so a situation here, ada this person which is a diver, dia drops tau. Dia drop from a board which is 10 meter above the water surface. Macam pernah tengok kan, which is in free fall. So maknanya kita boleh solve guna free fall, solve using free fall technique which is kinematic, or you can use this one. Okay, now, so drop represent kita akan ada kinetic energy equivalent to 0. So, at this location, kita akan nampak energy are purely dalam bentuk potential. So, that's why they write down as potential, mgy. Jadi, kalau kita substitute sikit-sikit lah, mg times 5. Dalam case ni, times 10. Okay, you will find that the water surface is noted as 0 height dia. Jadi, by neglecting air resistance, so means that friction tak ada lah. Friction tak ada. Using conservation, find the speed 5 meter above the water surface. Jadi, apa dia akan buat adalah, dia akan buat comparison. Dia akan ambil dua position, number 1 10, number 2 dekat 5. And then they are going to compare their energy. Iaitu energy dekat 5 dengan energy dekat 10. Okay, energy 5 minus dengan 10. Alright, cuma rather than dia letak sebagai final minus initial, dia susun sebagai final equivalent to initial ataupun initial equivalent to final. Okay, nampak cross lah ni, tak kisahlah. Okay, so sekarang ni the issue is all about referring to location mana yang initial dengan final. So dalam kes ini, initial are given as at 10 meter. And here is at 5 meter. Okay, tengok So, at 10 meter, the energy yang nampak adalah only mg y saja. Y ni adalah 10. Kinetic adalah 0. Kita dah bincang tadi And you find that at the location in between them, which is 5 meter, the y now turns to be 5. And this is the velocity at 5 meter. At 5 meter. Right, so maknanya dekat sini ada combination of kinetic plus potential. Okay, so another way of looking on how to solve. Jadi kita nampak bahawa the process required is independent, tak bergantung pun pada mass. That's the reason why mass of the guy just now tak diberi pun. Potong, simplified, substitute and then get the answer. Alright, now my aim of this example, okay, look closely at this example, is that so aside having energy final minus energy initial, if there is no friction, sebenarnya you can opt as energy at one location equivalent to energy at the other location. The same as what you have seen earlier. Okay. Now, the next question, find his speed when he hits the water. Maknanya, kita akan buat comparison. You boleh buat 10 dengan 0 atau 10 with 5 and 0. No problem at all. Okay, so kita tengok apa yang dia buat comparison. So, comparison dia adalah between two location similar to what we described earlier. Kita ambil dekat position 10 meter. Kita write down Ni 10 meter. Ini 10 meter. And here as at 0 meter. Jadi kita tengok types of energy. Types of energy at 10 meter is purely height potential sahaja. Purely U sahaja. Tak ada KE pun. K is 0. Okay. Or KE is 0. And then at location on the ground ni, on the water surface, all are fully converted. Yang ini akan jadi V maximum. V maximum upon reaching the ground. And potential adalah 0. U dia kosong. And then substituting, you will get the answer as 40 meter per second. On the other hand, let's say that you nak guna kinematik. Recall back that you might solve using kinematik for this one. So, macam mana nak guna kinematik ni? Kinematik adalah involving V. You could use this version, tapi you need the time. So, mungkin you would like to use delta Y. Delta Y UT tak boleh. V squared is equivalent to U squared plus 2AY dengan consider that Y is delta and also A is negative 9.8. Then U is 0. So, you will still arrive with 14 meter per second. Okay, let's wrap up our ideas. Okay, we're getting back to the book itself. So, you could either write it as in the form of delta plus delta plus delta, or you could either write it as the amount of energy at one location equivalent to whichever that you choose. Faham Alright, now this is the case whereby you are going to see situation where involve friction. Bila involve friction, you will find the first scenario. Not the first scenario. You will find that there is energy loss. Bila energy loss nanti, you akan nampak the amount of work would be negative. Okay, cumanya, you notice that kita akan start with external force. So, external force ini kita akan buku sebut sebagai other forces. Other forces ni external lah. Okay. Now, technique used by the book adalah dia buat summation. Ni summation of all the forces and then kita buat dot product towards dr. Okay. Cumanya, okay, when you go through, you akan nampak this version. Saya nak cantikkan sikit lah. So, how? You have seen here this expression earlier when we introduced. Cumanya, previously saya sebut sebagai work net equivalent to change of K, okay, or KE, okay. Now, work net, if you remember, adalah using the concept of F times dot R, kan, dot delta R. Okay, I like you to consider this, that this is net, including friction. Okay, including friction. So you will find that it's actually much easier than this one. Ataupun you boleh pakai this one or this one. The same thing. Okay, the same thing. Cuma cara berfikir dia sahaja. How you think about the situation is a little bit different. Or approach. Okay, sekarang kita tengok macam mana kita nak solve. Okay, 8.5. Example where there is a block pulled on a rough surface. Now, a block is initially at rest, pulled to the right ke arah kanan, horizontal surface, a constant horizontal force of 12 Newton. Okay, so kita nampak ada satu additional ataupun external force here. So bila kita nampak external force ni, external force ataupun kita kata applied force, straight away kita nak pakai work energy theorem. Ini work energy theorem sebenarnya. And then by using work energy theorem lepas ni, maka kita akan gunakan work sama dengan change of KE. So this is work net. Alright, I'm going to show you my technique and then kita akan proceed with looking at how the book itself solve. Okay, so the question is, if the distance traveled is 3 meter and then coefficient of friction is as much, okay, what will be the speed? Okay, what will be the speed? Alright, since I did say that kita nak guna version kita dahululah, my version. So I'm gonna jot down as work net is equivalent to change of KE. Why change of KE or what change of K? Alright, sama saja change of K symbols dia. So we expect that this one becomes half M and then V final squared minus the initial squared. Alright, now however the work net ni kita akan guna force dia adalah force net lah, and then dot product with delta R. Okay, so sekarang kita nak sub numbers. Delta R tak ada issue. We do have the same R. Kita factorizekan dia. So dapat 3. Tetapi when you substitute the F ini, you akan nampak bahawa according to the force, kita ada 1 to the right which is equivalent to how much? 12 Newton. Ini ke arah kanan 12 Newton. And then friction is adalah mu kali normal force. So mu pula nilai dia adalah 0.15 and then normal force dalam kes kita is a flat surface and then we have the force horizontal, jadi force tak akan influence the N. Jadi maknanya memang betul-betul sama dengan mg. So mu kali mg. Alright, macam mana kita nak substitute? Kita akan masukkan this force of 12 Newton minus the friction. Maknanya kata 12 minus 0. Coefficient just now 0.1115. Okay, so 0.15 and times the normal force which is mg. Alright, and the whole thing here need to be solved first, then only times with 3. Okay, times with 3. Now notice as well that the net force here, okay, kita buat tolak. Okay, kalau kita buka balik, kita akan tolakkan friction because work by the friction would be in the opposite direction. Okay, itu yang kita akan nampak. And then times 3 ni kita akan dapat sebenarnya with cos theta which is cos 0 sebenarnya. Okay. And then in terms of the mass, okay, substitute accordingly to the question. So mass is given as 6 kilogram. So this is 6 kilogram. The initial and the final. Okay, this is the one that you are looking for. But how about the initial? Initial ni dia dah sebut, dia kata at rest. Initially at rest. So this has 0 value. Okay, so you solve this, you are going to arrive with the answer which is 1.8 meter per second as well. Alright, now sekarang kita nak tengok technique used by the book. Alright, technique used by the book is it's separating the energy, the work itself. So you find that the idea of change of kinetic energy plus change of internal, which is actually friction. This is actually friction. Okay, then you will find that the change of KE earlier, change of KE. So this is this and this is this. Alright, so a little bit different whereby nampak positioning dia sahaja sebenarnya. If I did move it to the right here together with work FD just now, so you akan nampak bahawa dia akan jadi minus. So minus dia akan jadi 12 minus dengan when you do the work dia is as if macam work by the force external tadi and then minus with work by the friction. Okay, kita tulis sikit boleh? So kita akan nampak bahawa change of KE or change of K is equivalent to FD, okay, minus coefficient times mg kind d just now. So what you seen here is actually F minus friction and then times d. Alright. Cuma dia tak tunjuk cos kan. Tapi nak tunjukkan cos angle tu because they are parallel, right? So ada sebenarnya cos 0. Okay, the same technique and you will arrive with the same answer. So choose one that you feel senang nak faham. But for me, if you're choosing this one, bear in mind kita ambil work net. Now, the B question is a little bit tough. Why? Because this is the situation where object now being pulled by external force at an angle. Effect bila dia ada angle, we will find normal force changes. Dia tak boleh jadi mg. So, effect to the normal force just now, in the y direction, if net force is equivalent to 0, maka kita akan nampak normal force is actually susun balik normal force plus F sin theta. Kenapa F sin theta? Remember that this force, when we open up, dia akan bentuk dia ke sini. Okay, so F sin theta plus normal force. Okay, let's go back. Plus normal force F sin theta. This is F sin theta. So number 1. Number 2, normal force. Number 3, minus weight, right, in the y direction. So you have it in the form of this one, and when you simplify this one, normal force sekarang dah jadi kurang. Kenapa saya sebut kurang? So, kalau previously is just mg, now you minus with F sin theta. Maknanya F tadi, force applied at the angle above equilibrium tu, above horizontal, dah membantu untuk kurangkan tekanan pada permukaan. Okay, right now keep this. So this is the n value. N value ni kita nak pakai waktu y, waktu kita calculate the friction. Mu kali normal force. So which is friction. Alright, before we proceed, let's look at what the question itself all about. Right. So since force now is applied at an angle, as seen here, at what angle? The question is you should find the angle where the force then be the largest, where the force would result the largest speed, and the distance travel is 3 meters to the right. Now, expression that we're going to use, so stated here, number 1, work energy theorem. And for your information again, this is actually coming from friction. And now we are going to follow suit the given expression, and then we are going to see that it's actually related to what we have seen. No big deal if we choose it the other way around. Okay, now, so from here, the change here is this one, right? Now, observe that the initial kinetic energy is 0, so no question regarding that. And this one, notice that is a positive, alright? Because it's on the left side. But if you did bring it to the other side, then it's similar to what we have learned earlier, that friction, when you do the calculation, work by the friction, you will find that you are incorporating frictions times displacement and times cos 180. So it makes sense that if we did consider writing in this version, okay, last work non-conservative, we will find that this expression will leave us with negative product of frictions, okay, negative work product belonging to the friction as this, right? So meaning that our understanding from the very beginning, there's no problem. Or if you insist to follow the book, then you will arrive at this one. Alright, the main thing of solving is this one. Alright, the moment you simplify in this version, work final minus work friction, work by the friction, I like you to observe your substitution that it becomes FD, the force just now, but in the component parallel. So cos theta is parallel to the surface or parallel with the direction of displacement. So cos theta, yeah. Now, what we are going to do, we are going to differentiate, right? Towards theta. So towards theta. So based on the expression, okay, so on the left side FD cos theta minus micro times coefficient of kinetic friction times normal and time displacement. Okay. Now, when you differentiate toward theta, you have to remember that cos, when it's differentiate, it turns into sine theta. Okay, negative sine theta. And here, sine theta will now turns into a positive cos. So the negative stays. Now, how about mg? Now, observe that mg turns to be 0 because it has no product of angle. So differentiation only then be towards anything that has theta. So that's how you arrive at this one. And once you have understand how to differentiate, okay, the whole expression will be to be simplified with dividing it with force. Factorization lah, factorization. So this and this. Alright. So that's how you arrive with this expression. And from this expression, you can simplify and getting the idea that tan theta is actually sine theta divided with cos theta. So this one, from this one. Okay. And then what you do is you substitute the value of the coefficient just now, arriving with this is the number, angle, value maximum. It must not exceed